I don't have a normal distribution? I don't even know what that means. And I have to get this analysis done. Man, I am so skewed. Already, I'm going to give you a working understanding of data distributions. I'll explain them, those distribution-y things, why they're important, some different types of distributions, and more. I'm not going to cover everything because there's like a lot in the everything, but you'll be comfortable in most product development situations after this video. So I'm going to launch these disks off this launch, and whatever bin the disk ends up in, that's the measurement. That's the data point for that disk. Yeah, I built this. It's a prototype. I'm thinking about making an acrylic one in the future, for future videos at some point. Suffice to say, I took some of my maker time that I would have used to make some mountain art probably, like that stuff, and made this because you are awesome and I wanted to be able to show you this stuff in a nice display sort of way. Not that this is a nice display yet, but imagine it in the future. This is product development. Anyway, I'm going to launch some of these disks and it's going to take a while probably, so prepare for some sped up video. Okay, what I've made here is a histogram where each data point gets thrown, or in this case launched, into a bin. And we can do that with continuous data. Continuous data is the kind of data you can break up into smaller and smaller bits. For example, a hammer may weigh 3 pounds, or could actually be 3.7 pounds, or 3.72 pounds, and so on. It's continuous because the value can be anywhere in that measurement scale, sort of to any decimal, for example. The number of hammers, however, is not continuous. We can't have 3.7 hammers. Unless it was some sort of rating system for carpentry. It's an ambitious piece, harkening back to the mid-century style with an Indo-European cross-cultural influence. I'd give it 3.7 hammers. For the histogram, we put the data into the bins to see how frequently the data occurs in that bin. If I had much smaller bins, it would take a lot more disks or data points to build up to see the shape. That's what the histogram does, is they allow the visualization of the data and to get a sense of its shape from some finite number of data points. So this shape is a data distribution. It's how the data is distributed. The most well-known distribution is what's called a normal distribution. It's a bell-shaped curve. But not all bell-shaped curves are normal distributions, just so you know. Often they're normal enough for what we might need them for, but they're not necessarily actually normal. Now, normal distribution is the most well-known because it occurs a lot naturally. It's almost occurring here, for example. And the reason it occurs a lot naturally is because of a thing called the central limit theorem. Now, I cover that in this video short, but don't worry about it too much. Really, what I wanted to say is that there's a side effect of the central limit theorem, a corollary, if you will. And all you really need to know about it is this. When something is being measured, whatever the data is about, it has a lot of factors that impact it. And they all sort of average out, all those sort of different impacts on it, into a normal distribution. For example, if you're throwing a slice of pizza, that really was uncalled for, and measuring the distance, there's a bunch of muscles that impact it. There's the mechanics of your joints, the orientation of the pizza, and a bunch more. If you threw a bunch of slices, you'd probably result in a normal distribution. So why do we even care about distributions? Well, here's something I have noticed in product development. Sometimes when product developers are doing some statistical analysis, the distribution of their data is sort of an afterthought. They get so into the statistical tests that they only thought they put into the actual distribution is if it meets the assumptions of the statistical test. Often, is it normal or not? And that's actually the complete opposite way that it should be approached. We choose the analysis to fit the distribution, or the natural phenomena that's happening. The distribution is at the core of it. It's not, I'm gonna hammer in this pointy piece of metal. Oh wait, I can't, it's not a nail, it has threads on it. I'm gonna have to transform it, so it can be a nail or nail it in. So I'm gonna have to shave off those threads off the screw. that's just backwards. It's what do I have? Oh, I've got a screw. I should use a screwdriver, right? So if it doesn't follow a normal distribution, the next step is not to figure out how you can still treat it like a normal distribution. The next step is to figure out what do you have? And even more importantly, what's giving you the data that you've got? What's giving the data the shape that it's got, right? Now, this doesn't mean that you'll never use a test that assumes normality when your results are not normal. It's just that shouldn't be your assumed course of action, just going right into the analysis, like, oh, I'm gonna make sure it's normal. If it's not, I'm gonna turn it normal. That's really not the point. The distribution is at the center of what we're doing in the statistical analysis. It's like the thing. The analysis helps us understand the distribution, what's driving its location, what's driving its spread, what's driving its shape. Will it result in a happy customer? The data distribution is the embodiment of your product's performance. It's actually the thing you're going after. And we can learn from the distribution shape itself. So say, for example, you're measuring parts that are coming from a vendor, right? Your sort of incoming inspection. And the data has a nice curve to it, but then drops off abruptly. You can be pretty sure the vendor is screening out a bunch of parts during quality control, which, by the way, that's not necessarily an awesome sign. Just a heads up. Also, distributions allow us to make predictions, like the capability of the product, or on a market size, or whatever the application of your data is. Also, distributions allow us to do a thing called Monte Carlo simulation, which is really another type of prediction, but it's an advanced type of prediction or forecasting method. And yeah, knowing the distribution allows us to do certain statistical tests. Often it's, we'd like it to be normal for that statistical test, but there are many others as well, and those are also very valuable. Now I'm going to go into some of the other distributions, but first there's a differentiation, a delineation, a distinction I should make. In a sense, your data's distribution isn't ever a normal distribution, right? Nor is it any other of the distributions that I'm going to cover. It's just the distribution it is. It doesn't have a name. You can name it after yourself if you want. What on earth am I talking about? Well, say we tested some prototypes, like this one, and got a sample data set. It represents a larger population of data that theoretically exists if we could, measure everything, infinite number, or however large the population is. But we can't, so we've got a sample. And when you've got sample data, we try to identify a distribution that will best represent the full population, right? The full population from the sample. We can't be sure we've got the best representation, but we do what we can, and we're typically pretty close. So we check on our sample, and we find out that it lines up pretty well with a normal distribution, or some other distribution, but we're going with normal right now. So we move forward with our analysis, assuming the full population is a normal distribution. But it's not, because a normal distribution is a mathematical construct. It's a model. It's not the real data. It's a model, and we need a model, that mathematical construct, because we don't have the real data of the full population. A lot of statistical testing requires that we use a distribution to model the data. Check out my previous video on parametric versus non-parametric testing. Anyway, we use that model, the normal distribution or whatever other type of distribution, as that mathematical construct to be able to analyze the data. Alrighty then, let's go into some other distributions for continuous data. There's the Weibull distribution. It's a pretty flexible distribution that's good for modeling product failures, both early and late life. So it's used a bunch in reliability testing. There's the uniform distribution. There's an even chance in a uniform distribution of getting each of the values in some range. Now you might think this is a common one, but it's actually not really so common for continuous data. It can be very common for what's called discrete data. We're rolling a die, for example. There's an even chance of getting each of the numbers, but you're not going to get a 3.7 on a die. It's discrete, 1, 2, 3, 4, 5, 6 on a 6-sided die. The only uniform distribution I could come up with on a continuous data is a wheel, like where on the tire the car will stop. If you have any ideas of continuous data with a uniform distribution, please make a comment about it. There's exponential distributions. They're commonly used when the probability starts high and then rapidly drops off. A very common one is for timed events. So a tech support team might have an exponential distribution for the time it takes to close a ticket, right? They're able to close a ton of them very quickly, and as the ticket open time gets larger and larger, there's fewer and fewer that are open for that long. There's bimodal distributions, meaning that it's got two bumps or two modes, bimodal, of mean, median, and mode fame. Now, more generally, there's multimodal distributions. That is, there's more than one bump or mode. It's not typically a distribution to itself. It's more often a sign that something uncontrolled is merging two or more distributions together. For example, say you put a luminometer in a room. No, it's not to measure nearby Illuminati. Let's just call it a lux meter. No, it's not to measure how lucky you are. Okay, I'll just use light meter. For example, say you put a light meter in a room and have it automatically measure the light every hour for a week. And at the end of the week, you look at the data and it has two peaks. You were expecting there to be one peak close to zero for nighttime, very low light, and then trail off as the daylight hours were spread across the rest of the range of the data. Now, the nighttime peak was there that you expected, but there was also a very distinct and sharp peak about halfway up. And the data you're thinking must be wrong. There'd have to be the unnatural light source. So the uncontrolled factor of light switch added a secondary distribution, making it bimodal. Now, there are a lot of distributions for continuous data, and even some for non-continuous data. For example, a Bernoulli distribution has just two possible outcomes. Like flipping a perfectly fair coin would be a 50-50 Bernoulli distribution. If you were about to flip the coin 10 times and count how many times you got, say, tails, the likelihood you would get each number, anywhere from 0 to 10 tails, would follow a binomial distribution, right? So do you get 4 tails, do you get 6 tails, do you get 8 tails out of that 10? Binomial distribution. Now, my example is a 50% chance of getting either outcome, heads or tails, but it doesn't need to be that way for Bernoulli and binomial distributions. There just needs to be two possible outcomes for the test. One of those outcomes could be much more likely than the other. If it was an unfair coin that got 70% tails, for example. So I gotta come clean. And by that I don't mean I need to go take a shower. I mean I have something to tell you. I'm not making any statement one way or the other about my cleanliness. I've been avoiding using a specific word so I don't scare some of you off. And the good news is that I'm pretty much done talking about it, so it doesn't need to be scary. And that word is probability. Or in this case, and in this context, probabilistic distribution. Now, those different types of distributions I mentioned, the normal, Weibull, etc., those are probabilistic distributions, right? So for a normal distribution, imagining that bell-shaped curve, it means that any new data point is more likely or probable to come from the tall part in the center rather than those short part in the tails. Okay, so I have covered a ton, and I didn't even get into skewness or parameters. If you've got this far, please like and subscribe. I mean, if you got this far and you don't, you're killing me, Smalls. So, please, what's a guy got to do? Like and subscribe. Thank you very much, and have a great day.